Disruptors and curious minds, welcome to another episode of Thinking on Paper. My name's Jeremy. This is Mark. We unpack the future with the people that are building it today. Mark, what are we talking about? What are we getting into?
Oh, and tell Jeremy I've brought a spoon to today's
goodness.
show, a teaspoon or a coffee spoon. I bought a spoon because one of my very first memories of space was this analogy for neutron stars, that if you could somehow scoop up a spoonful of neutron star, it would weigh as much as the Earth or something absurd like that. And ever since I first heard that, it's always been there in the back of my brain, going, wow, like, that's just so nuts. It's maybe the first time my brain malfunctioned trying to understand the grandiose nature of nature.
Shouldn't we be more open to seek that malfunction? Like, I think
Yes.
a lot of times we're scared of that malfunction, and we think by that event occurring, we're not doing something right. But I say we got to do more malfunctioning to get deeper understanding. But that's a sidebar, Mark. Neutron stars. Why'd you bring up neutrons?
I brought up neutron stars because our guest today is Katia Moskvitch. She is a technology writer, a journalist. She is European Science Journalist of the Year for the year 2019 when she was business editor at Wired magazine. She has just finished working for the World Economic Forum as an ambassador on quantum. She was the quantum ambassador at IBM. She's written for the BBC. She is the perfect guest for Thinking on Paper. Today it's a story about chasing your curiosity. Welcome to the show, Katia Moskvitch. It's a pleasure to have you. Thank you for Thinking on Paper with us.
Thank you so much. Pleasure to be here. Hi.
I didn't mention that Katia also wrote the book, I think, on neutron stars, the quest to understand the zombies of the cosmos.
Yeah, neutron star matter is, neutron stars are very dense. They are the densest objects that we know of before black holes. So the densest objects made of matter, actually. So indeed, if you could scoop up a teaspoon of neutron star matter, it will pull you down with like, I don't know, 10 million tons or such like, but it's very, very heavy.
Well, Mark has a bad shoulder too, so that would be a bad thing. Your background, I've seen you reference with two words, science communicator, and I think that's a very important grouping of words because there's the depth of science is way beyond what a lot of individuals dedicate time to understand. And you got to have people that are great communicators to turn really complex thoughts and ideas and theories and maths into something people can understand. What makes a good science communicator?
Oh, that's a great question, Jeremy. I mean, for me personally, and yeah, I don't want to speak for everyone, but there are science articles out there that you read them and you're like, I'm not sure that was written by somebody who actually understands what they're writing about. And for me, that was always a big deal. I always wanted to understand exactly what I was writing about to be able to communicate it to others. And as a science journalist, well, I started my career at the BBC, and that's, of course, you're writing for everyone and anyone out there. It could be children reading you, it could be lawyers reading you, it doesn't matter, education. And so you have to be able to explain it in a very high level terms, but super accurate as well. So it depends on the reputation of you as a science reporter, science communicator, and reputation of the outlet that you're working for. And for me, it was always very important. And still, after my kind of BBC, several years at the BBC, I decided to go freelance and really go deep into reporting on physics and astronomy specifically. That's something I've been drawn to all my life. I actually wanted to be an astronaut at some point as a kid. That didn't happen, but I thought if I can't go to space, I will write about space at least. And so I was writing more and more about science and astronomy and more complex actually features for Quantum magazine and very sciencey outlets. And writing those stories made me kind of pause and think, okay, am I actually fully understanding what I am telling my readers? And I caught myself thinking, actually, no, I'm not fully understanding what I'm writing here, and that's not okay. So kind of mid-career, I decided to get a physics degree. I already had some background because I had engineering bachelor's degree, which helped, but not fully.
What discipline of engineering?
Mechanical engineering, and I focused on aerospace as well. So that was, again, my love of space. But after that, I did a master's in journalism. I knew that I wouldn't be an engineer, so I went straight into journalism. And actually, that was a really great career advice given to me by a Canadian journalism school faculty director who said, finish your engineering degree first, because it will really serve you well as a journalist afterwards. And that was brilliant, because then I I was able to write about science and tech, but not so deeply about physics. So I decided to go and get a physics degree exactly for that reason, because I thought that, being a science communicator, you really have to know in depth what it is you're writing about. So that helped me immensely. And I know that good science writers, communicators, they do understand science, and that's very important.
Jeremy, you need to go back to school and do a physics degree. Thinking on Paper will pay for your enrollment fees.
Oh,
I agree with you at the beginning when you said that a lot of people don't necessarily understand what they're writing about, and I think AI, that's only going to get worse. If I don't understand as a reader, then they obviously haven't embraced the Feynman concept of explaining it to a 5-year-old. And I don't think we should be explaining things as if you're 5. I think that's undervalues an adult's intelligence, but I think we should be explaining things clearly, accurately. What did you learn specifically at the BBC about how you write, how you think about, how you research, and how you draft a particular article?
Well, at the BBC, actually, the concept of explaining to a 5-year-old really stands, because you really have to be able to explain to a 5-year-old. And I think that's brilliant. I mean, we would always use what we call the pub test. So if you go into a pub and you're able to get your friend interested in what it is you're writing about, then you're fine. Other people use grammar test. If your grammar is able to follow your reasoning, then you're fine. But I think 5-year-old is even better. I have an 8-year-old kid, and he is super into science, and I'm glad that he is. But if I'm able to explain it to him and also his friends who are not maybe necessarily into science, then I think everybody will understand what I'm writing about.
I think there's something there too that's really important that I think you hinted on, that's helpful to be inspiring without forcing it. Mark mentioned Feynman, Carl Sagan is another one that just inspired a sense of wonder as he wrote, as he explained things. And that, to me, like, great writers, great science communicators can inspire a bit of a sense of wonder, but also take you down these further rabbit holes of discovery, right?
They make you want to know more. A bad writer will put off the reader, and the reader will go, no. But yeah, a good one will almost force the reader to want to keep going further.
Yeah, absolutely. I think that's super important. That's why I went into feature journalism too, because when you write news articles, I think it's much harder, because you're just covering what's in the moment. You can still do a really good job, and you can still interest your readers to pursue science career. But I think once you start connecting the dots, connecting different things that are seemingly unrelated into one story, so you actually keep the reader engaged to the end. And if you can take them places, you don't necessarily have to travel there, but if you can describe what it is in that particular amazing location and what those people do and how they think, and you really get into researchers' minds and describe people as people, and not just science is not just, it's more than just discoveries. I think it's very much about human nature as well. And for me personally, one of the reasons I really like talking to different scientists is because it doesn't matter where you are. You can be in the developing world or in the most developed country on earth. The most important thing, the most interesting thing is the people who are making those discoveries. And I remember one time I was working, I had 1 year working on a fellowship at Nature, a Nature magazine in London. And the fellowship actually involved traveling to developing world countries, specifically seeking out those stories that are underreported. And that was the most amazing experience, because I remember I was in Nepal, in Kathmandu, talking to researchers who don't even have electricity all day long. They literally have solar panels on the Kathmandu University roof so that they can have internet intermittently, not all the time. It was crazy. And they're writing amazing papers, publishing in Nature and so on. And yeah, for me, that was kind of the most important part. And that's how you can inspire other people as well.
As an aside, where else did you visit when you were doing the fellowship?
So I did 3 big stories. So one was that Nepal, which also was ICTP Center of Theoretical Physics in Trieste. And that particular story was all about anniversary that they were having. So it was not super interesting in that sense, but it was just super interesting locations and people. Another story that was very, very interesting was in Argentina. And so that was all about Cosmic Rays Observatory, Pierre Roger, in Mendoza province. That's probably my favorite one from that time, because basically they were thinking whether to close it down or not. The observatory had existed for like 50 years. and that contributed enormously to the development of the region in terms of infrastructure development. Schools were built, even university, and jobs, of course, created, and so on. And they were trying to catch still trying to catch those super highly energetic cosmic rays. And that was about 10 years ago. So they weren't catching any at the time. So it was the real threat of closure if they wouldn't get more funding. And so that was a story that involved traveling to Buenos Aires, speaking to a whole bunch of researchers and politicians and students, and then taking a overnight bus to Mendoza. And from Mendoza, talking to farmers, how this array was built, why it was built, farmers who didn't understand why suddenly on their farmland they would have these buckets of water trying to catch some weird particles. Yeah, I was talking to one farmer who was saying like, yeah, I mean, I don't mind because I think at least it controls the rain. So like they were really clueless of what it was doing. But, still the research, I think, is super important. And visiting those locations in Argentina was really eye-opening as well. So
cosmic rays in the rain. Listener, we're going to get into LIGO and gravitational waves, and I think we're going to turn into Star Talk, Jeremy, and we're going to go talk about neutron stars. But before that, so you won European Science Journalist of the Year in 2009. What did that change for you?
That particular award, so I won 2 awards actually that year, and they were for 2 specific stories, and both stories are really important to me. So one was British Science Journalist of the Year, same year, and then European Science Journalist of the Year. One of the stories was on dark matter and how people have been trying for decades to find dark matter and just cannot find it, but still putting their entire careers to discover these elusive particles. And when lack of results is actually still important because you keep constraining your results more and more, and so you know where to look. And so that story was super, super interesting to write. And the actual concept of persevering in science for years and decades of your entire career, it's just, I don't know. It seems, especially now when everybody wants to get everything right away, and with AI you can get a result straight away of whatever it is you're asking. And those guys are looking for something for 50 years and then die, and still without knowing whether there is dark matter or not.
They'll be really upset if AI comes along and discovers what it actually is very quickly. Jeremy likes dark matter, don't you?
We brought up Vera Rubin quite a bit on the show, and giving her the appropriate credit, even when, not to get too political, but even when the executive branch in the United States decides to wipe some biographical details about how she persevered and how she pushed forward with these groundbreaking ideas in a world that didn't accept a lot of really smart women, which is tremendously unfortunate. But I like to bring her up a lot because I think she's really special.
Yeah, I agree. She's really great. That was one story that was super cool to write, and another one, and that one didn't involve any traveling, but still I talked to researchers in different locations, and that was super interesting to actually understand where those observatories are located and what they do, because many of them are underground and deep under a mountain or what have you. And the other story, the one for the European Science Journalism Award, that involved actually traveling, and I was also writing my book at the time, so it kind of was a combination. I was working at Wired and started writing my book on neutron stars, which took me to different amazing places around the world, and one of them was Australia. And so the story was on application of quantum computing for high energy physics, and it was all about CERN and quantum. And that was the first time I actually saw a quantum computer. I was in Sydney at the University of Sydney, and I saw the chandelier, and I was like, wow, that looks...
What's it like? Like, me and Jeremy are very jealous of that. We've spoken to a lot of people about quantum, and we've never seen a quantum computer. What's it like when you first see it?
It's very dystopian or steampunk, I don't know. Like, I would...
Very steampunk, yeah.
So it's just it's this golden weird thing, and it really doesn't look like a computer or anything, really. And so, I remember talking to the researchers, and they described how it worked. And I knew I studied quantum physics before, so I kind of knew the theory behind it, but I never seen one. So that was really, really cool. Writing that feature on how CERN, specifically CERN, was still is, but was just starting to use IBM's quantum computers for high energy physics purposes to find new particles, to find new models, and so on. I thought that was very interesting and inspiring. And that was also part of my book research, because in Australia I went to Parkes telescope. That is one of the most famous radio observatories for pulsar detection, even historically. It's still working now.
I want to have like a side conversation and have you be my technical writing coach to figure out how I can run around and see the world and learn myself and explain. It sounds like just a tremendous journey, like awesome.
Doesn't it? You just said about quantum computing and CERN, and we read Michio Kaku's book Quantum Supremacy. We spoke to D-Wave. It's all about useful everyday quantum, and then you say that it's heavily involved in finding new particles at CERN. How heavily involved? For example, when they found the Higgs boson or proved its existence, how much of a part did quantum computing play in that? Would they be doing what they're doing now without quantum?
I mean, back then, no, it didn't play, to my knowledge, any part in finding the Higgs boson. But in the future, quantum computers could really, really help high energy physics by sifting through data much faster. Because you just imagine these collisions, just like astronomical data, right? Like when you trying to detect something in astronomy, you also get this deluge of data, and same from collisions and particle accelerators. And just to sift through that data, quantum computers could be of enormous help to help you like find much faster something new. And it's not really happening yet, of course, because quantum computers are not there yet, but there are papers being written, and CERN is working with IBM on exactly that. But we are waiting until quantum computers become fully fault tolerant, and probably another 5 to 10 years or so, and we'll get there.
You heard it here first, 5 to 10 years. Stay tuned.
Yeah, we've definitely caught the quantum bug. I caught the quantum bug early, just quantum mechanics, just because of the wonder of it. Like we talked earlier about Carl Sagan and some other writers, Feynman, inspiring wonder. Some of the early quantum mechanical books that I read inspired wonder in that life is like, okay, we have this physical thing, this world that's governed by Newtonian physics, right? And then you have this world that we can't see through that lens of Newtonian physics. It almost seems magical. And I think that's the interesting part. You were an advocate for quantum technologies for a bit. Would you say that could be one of the biggest disconnects for people understanding the potential of quantum computers? Because we see the world in classical, we see the world in Newtonian. Is that the disconnect, do you think?
I don't know about the disconnect. I think the bigger problem is the hype out there, and reporters who are not able to present the picture correctly, unfortunately. And there's just so much information out there, and on quantum as well. A lot of the articles deal with qubits and trying to explain on a very fundamental level, basically just repeating each other. There are qubits, they're different from bits because there's entanglement and superposition, blah, blah, blah. Like we've heard it before. I think everybody's heard it before. Like if people who don't understand the first thing about quantum computers probably heard it before as well. But what we don't hear much, and this is where I think is super important to the message to get across to, especially companies, but also, young people who are going to become maybe business leaders or politicians or whoever. They all should be aware of the potential of quantum computers. So for me, the most important message, and that's kind of has been my journey, like my quantum journey personally, is to explain what quantum can do for you. So if you're working in automotive industry, can you use quantum computers? And if yes, then how? Like this is the question I think media should be able to explain. Or if you're, in pharma, or if you're in politics, or like, for example, in the UK, NHS right now, the health system is looking into quantum quite extensively. And I think they're doing an amazing job just to see how quantum can optimize the supply chain and how it can help with, drug discovery and so on. So this is what I think we should hear more of. And that's how you're going to get people.
Are the NHS still using Windows Vista? I would love to see the British National Health Service suddenly go from being quite historically behind the times, making that massive shift to using quantum computers ahead of the rest of the world. That would be very cool to see. Yeah. Is it all about data? If you're in pharma, if you're in agriculture, if you're in the automotive industry, if you're in finance, is it really about sifting through huge amounts of data or does it go
No,
beyond that?
well, it's not necessarily that. It's more just the world of probabilities and not certainties. So it's how you come to your desired outcome very quickly. So instead of doing, for example, if you were trying to come up with a new material and you need to arrange the atoms in your molecule in a very specific way, well, there could be so many different ways you can do it. If you do it a traditional way, then you have to go to the lab and you just do trial and error over and over again. You arrange your atoms, you create your molecule, and then you test whether that's what you need or not. But a quantum computer can simultaneously check all the possible outcomes and give you the right one. So that's the power of quantum computing, and that's how it's different from traditional computing. Just computes differently. It looks at all the probabilities at once, and that's the beauty of it.
It kind of takes the brute force approach away, which science has been brute force for so long, and what an accelerant to science that quantum could be.
I think it can be a game changer in so many ways, in so many industries, from finance to drug discovery to even like helping you understand if you're flying from Sydney to New York or whatever, what route you're supposed to take, like how much fuel you need to optimize the weight of your aircraft, for example, and find the best route. Then it will just look through all the possible solutions at the same time and give you the best outcome.
thinkingonpaper.xyz/quantum, and you can listen to all our interviews with IBM, D-Wave, IonQ, Horizon, our book club on quantum, lots more, where me and Jeremy listen to people who know what they're talking about quantum. So back to Spoon. You're in Australia. You're having your mind blown by a golden chandelier, the quantum computer. I want to add Tavir Rubin with Jocelyn Bell Burnell. Mm-hmm. And if you could tell her story first, and now how that interacts with your story from being in Australia, looking at a quantum computer, to the writing of Neutron Stars, The Quest to Understand the Zombies of the Cosmos.
So Jocelyn Bell Burnell, I met her actually. She's a fantastic lady, very funny, super approachable. And at the time, the year was 1967, right? And that's when we discovered the first pulsar. Well, she discovered the first pulsar. Her supervisor got a Nobel Prize for it. A few years later, she didn't, which in my opinion is super unfair. She's very cool about it, though. She just kind of says that was the time, but I think she definitely should have gotten the Nobel Prize. The way it happened is very interesting as well, because up until 1967, when she found the first pulsar, neutron stars were fully theoretical objects. Just to explain maybe what neutron stars are, first of all, for those who probably heard the name but don't really know what they are, I personally find them super fascinating. I know black holes are all over the place and everybody loves
I hope not.
But neutron stars are, as I think I mentioned in the beginning, right, that they are the densest matter that we can find in the universe. So like the final bus stop before the black hole. And they pop into existence after stars die, and not just any star, but very massive stars. So for example, our sun, when our sun will die, it will be actually quite boring, because what will happen, it will first, in the next 5 billion years or so, it will exhaust its nuclear fuel. When the hydrogen nuclei basically fuse together, produce energy, that's why stars burn. Once the nuclear fuel will be exhausted fully, our sun will kind of swell up at first to become a red giant and eat up Mercury, Venus, and unfortunately Earth as well. We won't be there anymore, but very sad fate. And the outer layers of the sun will become just a planetary nebula, but the core of the sun will become this very small object called a white dwarf, which will be the size of the Earth, but very, very massive. So actually also quite massive, not as massive as neutron stars, but still, like, imagine the mass of the sun, you put it in the object the size of the Earth, and that's your white dwarf. White because it's very, very hot at first, so we see this white light radiating, when it's super hot, then we can see the entire spectrum, all the colors as white light, and then with time it will become black and fade into oblivion, and we will, become a black dwarf, and we will never be able to detect our sun ever again. So if we were to detect it from somewhere else. So that's the fate of the sun, and rather boring deaths. But if you look at stars that are much more massive, more than 8 times more massive than the sun, to be specific, then once hydrogen fuel is exhausted, what happens is then when kind of these lighter atoms fuse together, they form heavier and heavier elements. So from hydrogen we get helium. From helium, we get carbon, then we get oxygen and, neon, magnesium, silicon, I think, afterwards. And finally, we get to iron. So all of this they fuse, they give off energy. And then at some point, when it gets to iron, well, iron actually needs energy. You cannot create energy by fusing iron nuclei. That doesn't happen. Iron is like the end point here of nuclear fusion. So what happens then, when the star is stable and you have this pressure from nuclear fusion counteracting the pressure of gravity, well, if you don't have fusion anymore, then basically gravity starts being the only energy source at this point. The core starts to shrink and there's no more resistance to counteract the gravity. And everything just goes boom. So protons and electrons get squeezed together and become neutrons. So there are a lot of neutrons, and the resulting object is this core, which is the neutron star. We see the supernova explosion all around because it's we can detect it in optical, of course, and it's super bright, can outshine a galaxy. There are about, I think, 2 or 3 of these supernova explosions that take place in 100 years or so in Milky Way alone. So stars die pretty frequently. And the neutron star that stays behind is this fascinating tiny object of about 20 kilometers across. So if you imagine a city, the size of Chicago or something, and you curl it up into a ball and you put all the mass of the sun into that tiny sphere. That's how dense neutron.
A sun massively bigger than our sun.
It could be 1 to 3 solar masses. That's the mass that could be shoved into a tiny 20-kilometer diameter sphere, which is a neutron star. Anything bigger and it will collapse into a black hole. So to remain stable, it has to have this very specific kind of mass. And it spins and it travels through space at high speed. So that's your neutron stars. And we didn't know they existed for real. They were theoretical for quite some time before Jocelyn discovered them. I think the first time they were theorized was in 1934 by Franz Zwicky and Walter Bade. And those 2 guys, they just came up with this idea, very correct idea, that supernova were due to stellar death and a neutron star would remain. But the problem was it was 1930s and, there were other problems at the time. So even Oppenheimer, he actually worked on neutron stars quite a bit before he got distracted by atomic bomb project and pulled in a totally different direction. He was the one who came up with the upper limit of the neutron star before it collapses into a black hole. So he did some really pretty important work. But still, it was again mathematical, theoretical. And then finally in 1967, back to Jocelyn, she was a PhD student in Cambridge working with her supervisor, Anthony Hewish, who was super passionate about discovering more quasars. Quasars are these active galactic nuclei that are super luminous objects in the sky, and they are powered by supermassive black holes inside galaxies. And we had just discovered them at the time, so everybody was like, wow, super cool, let's look for more. And that's what Jocelyn was doing. She was putting wooden poles into the ground and connecting them with copper wire to create this quite primitive looking array, so an observatory made out of wooden poles and copper wire effectively. I actually went there. It's still there. You can still see the wooden poles. Copper wire had been stolen and sold, unfortunately, but the wooden poles are still there. So anyway, she was looking through data one day and looking for these quasars, and suddenly she saw a very weird signal that was repeating, just a peak, and it was repeating a few times. And she thought, what is this? That's not a normal quasar signature. So she went to her supervisor, they examined it, and they thought those were aliens, like for real. They really thought for quite a few months that those were aliens signaling from somewhere in the galaxy, signaling the Earth.
This was late 60s?
Yeah, that was like this, and they kept it super hush-hush. They didn't tell anybody about the discovery because she discovered 3 more. So she discovered 4 in total of this.
A lot of aliens, oh dear.
Yeah, exactly. And so she named them, they named them LGMs, Little Green Men. So those were the names.
No way.
For the first signals that they got. And she was actually pretty upset. And when I was thinking about, today's interview, today's podcast, I even bookmarked here in my book. I'm going to read you a short quote from her because she said she was about to defend her PhD thesis in about 6 months or so at that time. And so she said, why would Little Green Men be using a daft technique signaling to what was and probably still is a rather inconspicuous planet? So that tells you about her sense of humor, but also what she thought about the project at the time. But of course, it turned out to be not aliens, and they knew, so they just analyzed and reanalyzed the data. And finally, the paper was published in February 1968, and they said that it was indeed neutron stars, and that was just the bombshell discovery and beginning of pulsar astronomy. It was super cool.
Amazing story.
What a cool story. Yeah, and another brilliant woman that I want to highlight too, that doesn't always get the highlights that she deserves. Jocelyn Franklin was actually part of the DNA discovery piece that she doesn't get a lot of credit for. The X-ray diffraction images of DNA was actually one of the things that she discovered, and that largely fed what Watson and Crick kind of put forth as well. So I'd want to shine a light on her, as well as Vera Rubin and Jocelyn as well. Those stories.
Is the culture of this changing in astrophysics and science? In your journeys, in your writings, are you seeing a change, or are women still being made invisible?
There are more women now, I think. And when I was getting my degree at King's College London, we weren't that many. It was me and another girl, unfortunately, and in the whole faculty of theoretical physics, at least at the time. So there are not that many, but while interviewing people for my book, I interviewed quite a lot of female astrophysicists, and it's great. And in terms of the recognition that they deserve, I think they deserve much more. And I think what happens is that I find that women are a lot more careful when giving interviews to media, when thinking what to say. They will check and double check and triple check. And sometimes I found that whenever there would be a paper and a woman would be involved, even if she would be the lead author, she would, for some reason, prefer that her male co-author would give the interview and not her. And that's a shame. I think they really should be a little bit more, outgoing or confident in what they're saying is correct. And I find that men just kind of, if they think something is true, they just go ahead and say it. But the woman will triple check first before saying anything, and maybe that's one of the reasons, and I wish it wasn't like that.
Agreed. Well, let's talk about new adventures. Been thinking about a lot just in life outside of show. There are always challenges and struggles, and like, what's the next thing that you're willing to struggle for? Meaning, like, what's the next journey that's meaningful enough for you to dive in to the hard research, to the interviews? You've got a concept for a new book that you're pretty excited about. I know it's new. You're still kind of working through it, but talk us through that a little bit and why you're excited about it.
Sure, yeah. Well, I definitely want to continue my work in quantum. I think quantum computing is super promising. Quantum mechanics in general is just such a fascinating field, and there's still stuff we don't know about it. And literally earlier today, I was talking to ETH Zurich University here in Zurich, Professor Renato Renner, about quantum foundations, and he said that there's just so much, like, researchers don't even agree when it comes to quantum mechanics itself. So there's just a lot of opinions, so to speak. So there's a lot we don't know. Despite that, the technology that quantum mechanics has helped us to produce, including quantum computers, is amazing. And it's not just quantum computers, because people may say, oh, but quantum computers are not, like, they're not here yet, which is not true. They're here very much. They're just not fully, like, fault tolerant yet. We still need to do some research, but lots of people think that we don't even have them, which is, again, goes back to raising awareness around quantum. But everybody knows that MRI is here. Many people have probably gotten an MRI, right? Basically, MRI is exactly, that type of technology that is here because of our understanding of quantum mechanics. Lasers, another. So you have this theory of quantum mechanics that works super well in terms of what we can actually, like, how we can move progress forward thanks to quantum mechanics. And then you have a whole different theory of general relativity, and they all started at around the same time in the early 20th century. And general relativity, has helped us enormously to take us, like, Jeremy, you were talking about Newtonian physics at first, right? And that was a really big thing that happened with when Einstein published his theory of general relativity, because it helped us enormously to explore space, with GPS and so on. So we've achieved a lot. And yet...
Can we get a Feynman, explain it like I'm five, snapshot of what is general relativity?
Well,
basically
it's very different from Newtonian physics in the sense that Newton, for centuries, we thought that Newtonian physics explained everything in terms of, like, absolute space and time. and that gravity was a force. But Einstein came along and said that it's not a force, but curvature of space-time. So everything is relative, and everything is very different from Newton. Gravity is there because of the curvature of space-time. And that's fully different notion, is also very incompatible with quantum mechanics, especially when you look at it in extreme environments such as singularities of black holes or Big Bang in cosmology. Scientists are trying to bring these two theories together into one theory of everything, or commonly known as theory of quantum gravity. And there are several models out there that seem to kind of work, like string theory or, loop quantum gravity and so on. There are experiments now that are being actually constructed as well to test quantum gravity, but we are not there yet. And for me, the idea of the new book is that the two theories, they're incompatible, at least in some regimes. We've achieved so much, like separately, if you look at them separately. And with technology, quantum computers of the future, who knows, maybe quantum computers will actually help us to go 100 years back and reconcile those two theories as well. So that's the idea, but it's still being developed.
It's a big mission. I love it. I'm excited for you to embark on that journey. Both theories separately do very interesting things, but coming together with both of them, they're very different in the worlds that they operate. Fascinating stuff.
2 weeks ago, we had Brian Norton on, and he didn't write. He was the
technical facilitator, is what
technical facilitator. He was the human in the loop of the first book written by AI. Claude wrote the book. He was the facilitator. He asked it to write a book, and it wrote a book. Your new book is going to be about quantum computing and AI and general relativity and the theory of everything. And it, like Jeremy says, it's a huge mission. Applaud it. I can't wait. And I'm wondering, how is your writing and research process, do you think, going to change from the first book you wrote in a pre-AI world? And in this one, do you envisage a big change in the creative process of the writing? And has AI changed how you approach writing about technology in general?
Well, I'm definitely not going to ask AI to write the book for me. Taking all the fun out of it.
Right?
Exactly. Yes.
For me, I mean, writing, especially creative writing like that, I think that's the most interesting part of it. Talking to people, AI is definitely not going to help with interviews or anything like that. Where AI could be helpful, I assume, is probably maybe with the narrative flow of future books. I don't know about my specific book, but just if you're thinking through how to connect the dots, because it can search these huge databases, it can probably connect the flow quite nicely for people. And I'm pretty sure that people are already using it exactly for that, because you can even see LinkedIn posts that are sometimes quite similar in style. I am thrilled to announce blah, blah, blah. And, and then it goes through bullet points and so on. It sometimes gets quite repetitive. So I would assume that people are using it quite a bit for that.
I think it could be interesting to use it to maybe identify potential rabbit holes that you can explore on your own. Maybe things that you wouldn't have seen that you could weave into and use the gray matter here, to really get your head around stuff. And I think that's the important piece. And Mark, you referenced this earlier. I want to hit this again for our listeners, like running into those moments where you don't understand and where your face is melting and, you're trying to get your head around something new. Those are the powerful moments. Those are the moments that we need to have to continue to grow, to continue to synthesize information. AI probably has a place, but don't outsource all of it to that.
I always think about the scene in Star Wars where Luke Skywalker goes into the Death Star run and he's relying on his headset to do all the work for him. And then Obi-Wan talks from beyond and he goes, "Switch off, Luke, turn off." And Luke eventually turns off the help. He turns off the guidance and he does it himself. And that's when he really, that's when he succeeds, isn't it?
Yeah, well, I think for me, AI is cool and is really useful as in terms of assisting us. I don't think AI is gonna ever replace us as humans. Creativity should be there for real, but relying on AI to help you connect the dots or help you think of something that you haven't thought about before just because you don't have access to the data, or for science as well, right? If you want to know, for example, if a certain paper has been written or not, you can't just look through all the scientific papers, even on a specific topic, but AI would very likely be able to sift through everything that's been written on, I don't know, neutron stars in this case, and find out where the gaps are. So that's super useful.
Very cool. I love it. I love it.
I think we have a question from a certain Mr. Kevin Kelly, do we not?
Yeah, why don't you tee that up, Mark?
It's a nice, easy, quick question, isn't it? What should humans be? And we like to add a little in brackets to that. And how does technology help us get there?
Well, I think that links very nicely to what we were just saying. I think humans should be humans, first of all. They should stay human. They should stay creative, emotional, empathetic, if it's now or 100 years from now or 1,000 years from now. Where I would like humans to get to with technology is I really hope that there would be a moment when we think of something that will help us to travel in space much faster so that we can start exploring other galaxies, other stars and planets and so on for real, not just looking at them through telescopes, because universe is huge. Milky Way is such a vast place, and we are just a tiny speck. So I think it would be really nice if technology of the future could help us to do a little bit more in terms of space exploration.
Well, Michio Kaku says we could just, put these little stations on all these far-flung planets and just beam our consciousness. So maybe that's how we get there quicker. No need to comment on that, but yeah. Speaking of consciousness, everybody, Mark and I are reading Irreducible, Federico Faggin, in the latest episode of Book Club. We're in melt face moments. We're in those moments where, holy smokes.
You need to be conscious when you're reading that book,
You need to be conscious when you read it. But a spoiler alert, consciousness is a quantum process. We are quantum and classical machines together. Thinking on Paper, XYZ, for all the shows, show notes, links, and all that fun stuff. Katia, thank you so much for joining us today. Love talking with you about it, and can't wait to hear more about this next book journey for you. Mark, closing thoughts.
Thank you for helping me with the spoon, and a teaspoon of Neutron Star keeps the dentist away, or something like that. I love it. I love the scope of the conversation. I love the book. I can't wait to read the next book. As Jeremy said, thinking on paper.xyz, to put all the links to your journalism, to your work at the BBC and IBM, and the book. And yeah, thank you. Stay disruptive. Be curious.
Keep thinking on paper.
Okay. Thank you.
Thank you.